Hi, let's take a look at how we can use Huygen's principle to derive the law of refraction, or Snell's law. Similar to how we derive the law of reflection, we're going to start with two light rays that are traveling towards a surface on a parallel path. However, both sides of the surface represent a transparent material. Material 1 is where the light rays start. Material 2 is where the light rays enter. And what ends up happening, once this light ray strikes at the surface A, the second light ray is going to be at a point B. So by Huygen's principle, this light ray is going to continue moving at the same speed in the same direction until it reaches the surface at point C over here. So the angle of incidence for this first light ray from my normal at A is going to equal the angle of incidence for my second light ray at C. And I'm going to get a 90-degree triangle here from point A to B to C back to A. And looking at my angles, my 90-degree angle is between side AB and side BC. So if this angle is my incident angle theta 1, then right here in this triangle, that angle between A, C, and segment BC would be 90 degrees minus theta 1. So that means that my angle between AB and AC is also my angle of incidence theta 1. Now, during the same amount of time, the wave traveling in side 2 is going to travel more slowly. So it'll travel a shorter distance, and we could trace out some arc that would represent where that ray would have to be after that same amount of time delta t. And we know that after this light ray, the second ray, strikes at point C, it's also going to enter the second surface, and those two rays would again travel along parallel paths. So D to C would also make up a 90-degree angle. So ADDC is a 90-degree angle, and ADCA is another example of a right triangle. Well, the angle from the normal inside side 2 at point A, we call our angle of refraction theta 2. So this angle inside my triangle of ADCA is going to be 90 degrees minus theta 2. So the far angle here between side DC and side AC is also my angle of refraction theta 2. So these two triangles share a hypotenuse, AC. So if I take a look at theta 1, the opposite side is side BC. So the sine of angle 1 is going to be BC over AC. And the sine of theta 2 is going to be side AD over AC. Well, AD and BC have different lengths. Their lengths are the speed of the wave inside 1 times my time of travel for BC, and for AD, it's the speed of the wave inside 2 times my time of travel, which is the exact same amount of travel time. Well, since these two signs share a denominator, that means that I can combine those two equations. 1 over AC is going to be the sine of theta 2 divided by the length of AD. So that means that the sine of theta 1 is going to be equal to BC times the sine of theta 2 divided by AD. And if I take the ratio of BC over AD, that travel time cancels out. It's totally arbitrary, just depends on letting the two travel for the same amount of time. So that means the sine of theta 1 has to equal the speed on side 1 divided by the speed on side 2 times the sine of theta 2. Well, with waves. We characterize the bending of waves and the wave speed through a material property called the index of refraction. And the index of refraction is the ratio of the speed of light in a vacuum divided by the speed of light in a material. So the speed of light in that material is going to be the speed of light in a vacuum divided by the index of refraction. So if I take V1 and divide by V2, I would have C over N1 divided by C over N2, and to make that a proper fraction, V1 over V2 is just N2 over N1. So sine theta 1 is N2 over N1 times the sine of theta 2, or, in the way we're more familiar seeing with Snell's law, N1 sine theta 1 equals N2 sine theta 2. Thanks for watching.